Okay, so looking at the next set of homework, we're dealing with circular motion now. I've chosen out a couple of problems. Once again, I'm probably doing a few too many of these, but we'll stick with it for the time being. So one of the questions, it's a two-parter, and it asks, a model airplane of mass 1.2 kilograms is attached to a horizontal string and flies in a horizontal circle of radius 5.7 meters, making 2 revolutions every 7 seconds. Now this is something a little new compared to what we've done before. This is where they've incorporated some information about circular, or not circular motion, but rotational mechanics, and then it blurs with circular motion. They have in parentheses, the weight of the plane is balanced by the upward lift force of the air on the wings of the plane. So in short, looking from above, I've got someone who's actually swinging a plane, a model plane, around in a circle. And that circle has a radius, r, of 5.7 meters, and then the plane has a mass of 1.2 kilograms. Now here's where it gets a little bit more interesting. They say that it makes 2 revolutions every 7 seconds. 2 revolutions in 7 seconds. We're going to work with that here in just a moment. Okay. 2 revolutions every 7 seconds. It's the same thing as making 1 revolution in 3.5 seconds. All right. The weight of the plane is balanced by an upward lift force of the air on the wings of the plane. The acceleration due to gravity is weird. This one says 9.81. Fine, that's what I'm used to anyway. Find the speed of the plane. Answer in units of meters per second. Okay, so that's part 1. Part 2 is going to ask us for finding the tension in the wire. Okay, so part 1 is actually going to deal with how quickly the thing is moving. Now, let's go through and take a look at this. Now, for circular motion, it's one of the few places where we're going to treat it as though the object does not speed up and not slow down, but it does have a net force acting on it. Think back to when we looked at the bowling ball in the hallway. To change the velocity, not the speed, but the velocity requires an acceleration. And velocity, while we could keep going the same speed, velocity is a vector. To change a direction requires an acceleration. So we're going to have an acceleration and a net force on this object, but it will actually be going the same speed the entire time. And it's the speed that we're putting into our circular motion equation, because this is uniform circular motion. All right, what we need is the following. We're going to be dealing with, this thing goes around the circle twice in 7 seconds. So what we're going to do is we're going to find the speed that it's going, basically the distance it goes divided by the time it takes. The speed in this is not actually going to change. It's not going to go up, not going to go down. Our velocity is going to be changing the entire time because it's constantly changing direction. We do have an acceleration here, but that acceleration is changing the velocity by changing its direction. That means our speed is actually going to stay the same. And we can find our speed by doing distance divided by time, because this thing is not speeding up nor slowing down. All right. What we need is a distance. Well, we know that in 7 seconds, our time, it goes 2 revolutions. So what I need is 1, 2. Well, the distance around this is actually going to be the circumference. So the circumference of a circle is equal to 2 pi r, or 2 times r is our diameter. The circumference is diameter times pi. Now, we know that it's actually going 2 times the circumference in 7 seconds. So if I want to find the distance it's gone, I should be careful writing delta x, because our displacement is 0. It comes back to where it started. But our distance is going to be 2 times the circumference, which will be 2 times 2 pi r. We end up with 4 times pi r. Any way you look at it, the distance this thing goes, if you want to call it delta x, that's okay, is going to be equal to 4 times pi, which is 3.14159, etc., times our radius of our circle, which is 5.7 meters. Now, one thing that I do want to note real quick, 4 doesn't have any units, pi does not have any units, and the only units we have come from the radius here. We do actually get units of distance. Let's find out exactly how far this plane goes. 4 times pi times 5.7 equals, our distance is equal to 71.6, technically 3 meters. 5 meters is actually a pretty big distance for the radius there. In short, 5 meters, that makes the diameter, better part of 11 meters. That's as tall as the high school. So think about the lab that we did earlier this year when we were trying to measure the height of the building. It was actually comparable to this. So this is a very big circle. Goes a pretty big distance there. All right, now we've got the distance. We wanted to find our speed, which is v. Technically, it is the magnitude of the velocity vector. But our speed is going to be equal to our distance, 71.6 meters, divided by the time it took for it to do 2 complete rotations. That was 7 seconds. So we're looking at slightly over 10 seconds. One of the other reasons that I put this up here, I do not have any intention of telling you 2 revolutions. I would tell you the time it takes for 1 revolution. So you would just take the circumference divided by 3.5 seconds instead. But you should end up with the same number no matter what. 71.6 divided by 7. We end up with 10.2, technically 3 meters divided by seconds, meters per second. That's our speed. 10.23, let's see. Oh, that's not my solution key. Where is it at? 10.23 meters per second. Awesome. The next thing they ask us is for the tension in the wire. Okay? Before this, I'm going to need to draw a free body diagram of the plane. Gravity is pulling down on the plane, but they say that we have a force of lift. It's not one that we really talk about in class, but there are other forces that we haven't necessarily looked at yet. Airplanes get a force that is called lift, in which the air will actually push up on the wings. If you're interested in learning more about that, ask me about it sometime outside of class and we can look at it. We've also got a force of tension. What I want you to imagine is, if this is the top-down view, and we've got it moving in a circle like this, we're looking at it from behind here. That's an eye. And then we're seeing the plane going this way. So now I've got my force of tension pointed to the right. Well, the force of tension is a centripetal force. It is actually pulling to the right at this instant in time. Now, if I were to draw it back over here, I might have to change how I'm looking at things. But if I'm in the plane of the, plane, so I have the plane moving at eye level, this would be what the free body diagram looks like pretty much at any point with me behind it. Maybe on this side it might point off to the left or something like that, but if I'm standing back here. In short, this is a free body diagram that describes while the thing is going around. The easiest way to do it is just pick one spot in the circle, take a picture of it, a mental picture, and draw your free body diagram of that. We have the force of tension pointed to the right, force of lift is pointed up out of the board, and the force of gravity is trying to pull it down into the board. Would be a pretty good way of looking at it. Now, this is the direction that it's moving in a circle in, so my sum of forces in the x direction, the way that I've got it, is my force of tension, and it must be equal to my centripetal force, Fc, which is my mass times my centripetal acceleration, which is the same thing as saying my force of tension must be equal to mv squared over r. This is my centripetal force, the equation we introduced. All right, they want to know the force of tension. Well, we know the mass of the plane. That was, I set it aside somewhere over here, 1.2 kilograms. we found the speed just a moment ago, 10.23 as I recall. 10.2 meters per second, quantity squared, because it's mv squared, over r, which as I recall was 5.7. Is that right? 5.7 meters. Good. I plug these into my calculator, and I find that the tension required to pull this thing in a circle, 10.2 squared times 1.2 kilograms divided by 5.7 equals 21.9, should be newtons. I'm going to add meters squared per second squared. One of those meters cancels out, so I'm left with meters per second squared times kilograms. It is in fact newtons. Let's double check our answer for the force of tension. Let's see. 5A, model airplane. They get 22.0 newtons. It's a rounding error thing, but it should actually accept both of these because it's within 3 significant figures. All right. Here's applying some of circular motion.